Hello everyone, this is Darren, and this is our talk for Unit 2 on causal inference. And really this talk is going to be based around one of my favorite papers from Miguel Hernan. It's a structural approach to selection bias. And so in medicine, in epidemiology, we are almost always focused on this question of cause. If I do X, what is the consequence for Y? Now, sometimes we also get interested in prediction and developing tools to predict future risk. But right now, we're going to be laser focused in on questions of causality because we're interested in treatments. If you're a medic, you're interested in prescribing medicine or some procedure in order to prevent or improve outcomes, so the causal relationship. And the challenge with cause, as some of you will know, is that we can never directly observe causes. And what I mean by that is that the most common kind of definition of what a cause is called the counterfactual definition. And what a counterfactual is if you were to take, say, me, and you were to give me a treatment and then see what happens to me. The only way to really understand the cause of that treatment, because of things like regression to the mean and so on, would be to go back in time to the exact point where you gave me the treatment and then to not give it, let time go forward again, and then compare the outcomes in the two groups. And that's called the counterfactual approach to causality. And obviously we can't observe that directly. So what our goal then in terms of trying to establish the causes of outcomes, whether something X causes Y, what we try to do is to find two groups whose future risk of the outcome, if they're not treated, would be very similar, and then treat one of those groups. Once we've done that, what we're looking at is a statistical association between X and Y. Right, so we can never directly observe counterfactuals and causes. We kind of have to create these thought experiments and simulate counterfactuals and causes, and then make inferences about them from statistical associations. And so this talk is just about the causal inferences, and our previous talk was about statistical inferences. So we'll just be focused in on that. And so this sentence, and probably all of you have heard it at this point, correlation does not imply causation. Well, correlation exactly implies causation. It's not enough. It's not a sufficient thing to make a decision about causation, but it certainly implies it. And importantly, we never see causation directly. We can only infer it from correlation, so we have to take this quite seriously. And like when I get told the sentence, correlation does not imply causation, well, it's like telling a firefighter that the building's hot. Like the firefighter understands this is the risk and this is the hard part of the job, but we still have to go put the fire out. And the statistician, the medical researcher, the epidemiologist, we understand that correlation is not causation, but we still have to make causal conclusions, or else what is the point of what we're doing? And entirely too many researchers, they shy away from the word cause, and they refuse to admit that what they're interested in is cause, even though they're looking at associations. And so that leads people to not be very rigorous about making causal inferences. They just throw their hands up and avoid it altogether, even while they're making causal inferences. So it's just better off if we can kind of come up front, accept that we're trying to understand cause, we're trying to infer cause from association, and then to do the best job of doing that. And so that's really what this talk is about. It's about not hiding from cause and trying to understand some basic tools that will improve us making causal inferences. And at the same time, this is ultimately going to explain why randomization is so important from a causal inference perspective. So randomization is important for statistical inferences because it helps us meet our assumptions of independent, identically distributed data, but it's also critically important, and probably more important even, for the causal question. And so when we're talking about causal inference, what we're really focused in is the bias. Remember, we have an estimate, which is the center of the target. And there's basically two ways we can miss the target. We can have kind of random misses, which would be scattered all over the overall target, around the center. And if you were to average out those differences, they would all still land right in the middle. Bias, on the other hand, is a kind of consistent and systematic deviation from the center of the target. So here you see that, you know, all of the shots land in one particular place off the target. It's a systematic difference between what we're trying to estimate, the estimand, which is the causal effect of the treatment, and what we actually see in front of us, the estimate that we're going to use and make causal inferences from. So this is a talk about bias. And one of the hard things about bias in medical research and epidemiology is that over time, researchers have come up with all these different types of biases. And most of you will be aware of come across lists like this, like these are all the different kind of things that can happen. And the cognitive load of trying to understand what all of these different biases are, memorize them and everything else, you know, is overwhelming. Like, you know, it'd be very difficult. You know, you could spend 20 years in medical research, you know, and not be able to walk around with this information in your head. And so the great thing about the Miguel Hernan paper is it says, essentially, it simplifies that thing about bias. That it says that statistical associations essentially arise due to 3 structural relationships. And now we've only got to think about these 3 possibilities when we're evaluating our associations to make some kind of a decisions or inferences. And so those 3 structural relationships are that if you see an association, you are either seeing a cause and effect relationship, you are seeing the existence of shared causes, which we call confounding, or you're seeing the adjustment for shared effects, which we call selection or collider bias. And it could be some combination of these things. Right? So this is what everything on that biases list really comes down to being a type of confounding or a type of selection bias. And so if we can simplify how this works and what these things are, then it makes it a lot easier for us to understand bias. Of course, there's still chance. We still get a wrong answer due to chance, but that was statistical inference, and that's what, you know, we talked about in the last lecture. And so we have a really important tool for understanding how to find and then deal with these potential biases from confounding and from selection bias, and they're called directed acyclic graphs. So directed acyclic graphs came to epidemiology largely from the computer scientist Judea Pearl, who wrote this book called Causality, and has very recently wrote a book called The Book of Why that people have been very interested in and commenting on. And so in it, he describes this graphical method of trying to relate variables to one another in a manner that would allow us to identify potential confounding or selection bias, and then we can do something about that. And so then this stuff came into epidemiology in 1999, in the early aughts. And this paper here was Sandra Greenland and Jamie Robbins with Judea Pearl, Causal Diagrams for Epidemiologic Research, is a classic. And essentially, it's based on graphs. And so we have to have some kind of a language to talk about graphs. And so the first thing we have are nodes. And nodes are variables. So X could be height, for example, and Y could be whether you had a heart attack or not. And so we have nodes, and nodes are always variables in the sense that we think about them in day-to-day research. And then we have edges. And so in a graph, an edge is just a line that connects 2 nodes. And importantly, because these are directed acyclic graphs, we have directed edges, which means they're pointing in one direction or another. They're directed. All right, so that's the basic makeup of, you know, a graph. Nodes, edges, and directed edges. And now what we have to do is we have to deal with this issue of acyclic. So they're directed acyclic graphs. And acyclic just means that there are no feedback loops. No variable can cause itself. Now this isn't saying that the universe doesn't have no feedback loops. It just means that to use this tool, the DAG, as we're going to use it, it has to have a situation where there isn't a feedback loop. So this is a limitation to the DAG. So here what we have X pointing to Y, and then they have a shared, what we're going to call a parent variable C. And so in the DAG, the other thing we're adding is that every time there's a directed edge, it's us saying that this is a causal relationship. We don't know that it is, but we're saying that this is a causal relationship. We're putting it into the DAG, we're formalizing it, we're communicating it. And so here we're saying X causes Y, but also that C causes Y and X. But the important thing here to come back to again is that this is acyclic. There's no way for X, you follow along here, you go from X to Y. There's no feedback along the arrows back to X or any other variable. So C comes here and it stops because it can't go back through this arrow. Y doesn't go anywhere because there's no arrows emanating from Y. So this is acyclic. If we come here, we say this is acyclic because X can come up here to C, can come up here to Y, but nothing in C can come down here to Y, but everything stops in Y. In other words, there's no feedback loop. So this is an acyclic graph as well. Now we get here, would be called cyclical, right? Because I can go from X to C to Y to X. And so this kind of a graph, the rules that we're about to go through, they don't apply to this kind of graph. You'd have to come up with some other way to kind of break the cyclicity of the graph. All right, so directed acyclic graphs. So we said 3 structural relationships. So the first is that it could just be cause and effect, which is what we're interested in. So we see an association between X and Y. And this could be a correlation coefficient. It could be a regression coefficient. It could be a chi-squared test showing a lack of independence. Anything you can mean difference between two groups. We have some statistical association, and we're trying to understand, is this cause and effect? Well, it could be cause and effect, and that could be the explanation for why we see an association between X and Y. That's the easy one. And usually what we're trying to do is eliminate the other two explanations. Just like Sherlock Holmes, we get rid of the other things, confounding and collider or selection bias, and that leaves us with cause and effect as the only explanation. That's what we're trying to do. And at the same time, we have cause and effect, X causing Y, but it could be that Y causes X. And so we think about that a lot. And we think about that if you think about the Bradford Hill kind of list of things that he thought was important. The timing of things, matters quite a lot to try to rule these things out. All right, so that's pretty straightforward. Confounding becomes very tricky, and there's a long history in epidemiology of having a hard time deciding what confounding is. But confounding, basically, my favorite definition or explanation is this problem of confusing exposure effects, so the thing that we think is going to be the cause, with other extraneous effects. All right, so these things get mixed up. Our purported causes and other variables get mixed up, and their impact on the outcome, and we get confused, and we make bad decisions about what the cause is. And so confounding is this. It's when two variables share what we call a parent. And so in this case, X and Y both share C. And so if we have a situation, for example, where X is the amount of gray hair I have and Y is my BMI, right? Those two things are associated. If we looked at just me over the course of my life, I can guarantee my BMI has gone up every single year that my amount of gray hair has gone up. But will we conclude that there's some causal relationship between the color of my hair and my BMI? And the answer is, of course not. I wouldn't walk around, I wouldn't expect to dye my hair black tomorrow and then suddenly lose weight. There's no causal relationship there. I couldn't intervene on gray hair to make an improvement in my BMI, right? So it's kind of the silly example, the obvious confounder. The shared cause of gray hair and my BMI is my age, right? So what we have to do is we have to identify those kind of variables that can explain. So this arrow, we're asking, does this arrow exists? And that we see an association here. We want to know if it's causal. Well, the first thing we have to do is we have to eliminate these arrows, which are causing this from C, from my age, both my gray hair and my BMI, which would certainly result in a statistical association between the two things. Here's a graphical example of what we're talking about. It's a very famous data set about flowers, of all things. And here what we're doing is we're measuring two physical characteristics of the flowers, the petal width on the x-axis and the sepal width on the y. And if you were to do this, what you would see, and then you were to plot a correlation, right, or a regression coefficient, you'd see this kind of mild inverse association between the two things. So as the petal width gets bigger, right, as this gets larger, then sepal width comes down, it becomes smaller. And so you might conclude that that is the relationship. And you might try to make some kind of causal conclusion. But what's happening here is we're missing a piece of information, right? So we call one of these X, we'll call the X-axis X, pedal width X, and supple width Y, just for this example. Ask the question, is this causing that? Is this causing it to come down that? And so we're missing some information though. What we're missing is actually what we have are 3 different types of flowers, right? 3 different species of flowers. And you can see that those 3 species all occupy very different places in the overall plot, right? So that line before was coming this way, but if you'll look at what's going on within each actual species, the relationship is actually going up, right? So this is actually an example of something called Simpson's paradox, and what it means is that the relationship within each species is a very strong positive relationship. But if I don't account for species, then the overall relationship is inverse in nature. And so here, the biological relationship between the 2 size measures is that they're positively correlated within species. And the only reason we're seeing this negative correlation is because we're not accounting for the fact that different species have overall different levels of these 2 variables. And so that's creating this biased picture of it. And so what do? Well, what we do is we use statistical models to adjust for the confounder. And so we'll talk a lot more about linear models towards the end of the module, and we'll touch on them throughout. But what a statistical model does, what a linear model does, is that essentially if I adjust for species, I include it in the model. Then what I'm saying is to give me an estimate of this relationship between this association between X and Y within each of the things I'm adjusting for within each of the levels, and then kind of give me a weighted average across those 3 positive relationships. So at the end, I'd get a beta coefficient, a regression coefficient for the the relationship between pedal width and sepal width. It would be positive. So the regression coefficient would just be a weighted average of these 3 lines that would give me kind of the true relationship, really, between width of the pedals and sepals. All right, so that's confounding, and most people deal with confounding, fairly often. If you've done any kind of observational research, then confounding becomes super important. What I have to deal with is called selection bias, and this one can be a little bit tricky. And this is basically when an association in a selected sample is different from the underlying population. But there's a causal explanation that I think is very helpful to understand what's going on when we see selection bias. And so one of my favorite examples is from Marie Gleimer, and she tells us it's basketball, and I like basketball. And so imagine that we have a sample of professional basketball players, and we're going to have a simple model here where to be really good at basketball, it's strongly predicted by 2 things. One of them is to be tall. And I've read some statistic where if you're like 7 feet tall, there's like a 32% chance you'd be a professional basketball player if you wanted to, because being 7 foot tall is obviously very rare and very useful for playing basketball. You barely have to move if you're 7 feet tall to play basketball and score the bucket and block shots and all the rest of it. So being tall is a cause of being good at basketball. If I could make people taller, that would make them better at basketball on average. The other one that we're going to call is, we're just going to say, is got game, right? You just play the game. You have the mental ability to move fast, to pass the ball, to just do the things that has to be done to play basketball. So you can just play. You're just good at basketball. And so that's a cause. And so then the question becomes, what is the relationship between being tall and got game among the basketball players? Because what this causal model is saying here, I don't have an arrow between these 2 things, right? So I'm saying, if this is my statement about the universe, I'm saying that there's no causal relationship between being tall and got game. I'm saying both of these things do cause you to be good at basketball, more likely to be a professional basketball player. And so the trick here is when we look at data that's only in the basketball players, and then we see if there's a relationship here. And so the question is, given that you're a basketball and you're not tall, right? So you are a professional basketball player, but you're not tall, then what do you certainly have? And the answer is you've got game. And if you're a basketball player and you don't have game, then what are you? Well, then you must be tall. In other words, there's these two pathways to becoming a professional basketball player. And if you're not one, then you must be the other. So when we look at just the sample of basketball players, then what we'll see is an inverse relationship between being tall and having game, right? But that causal relationship. And so I can simulate some data. And here I've simulated some data. I've got height, and we'll just do it in standard deviation scores. And this is the height of some people. And then I've got game. All right. And so you can see there's the trend line here, the linear regression line, is essentially a slope of 0. There's no relationship. It's just a random scatter plot of points. And then I can simulate data that where your probability of being a professional basketball player are independently increased by either having game or being tall. And when I do that kind of a simulation, the red dots would be the people who make it into the professional basketball. And so you can see these people here at the highest levels of having game, they are the ones that tend to make it in. And these people here at the highest levels of height, they tend to make it in. And of course, if you were to then imagine fitting a line through just those red dots, what would you see? You would see an inverse relationship. And so this is what happens in the context of a research study, where instead of us selecting on professional basketball players, we're selecting on the people who come into our studies. And so if you have predictors of who joins your study, and that those things will start to be correlated to one another, even if they're not correlated in our general population that we're recruiting from. All right, so then how do DAGs help us with this situation, right? So how do we use DAGs as a tool to help us identify confounding and selection bias, or we call collider bias? And so in a DAG, these graphs, these directed acyclic graphs, the absence of an unblocked path, we'll come back to that, between two nodes, and you know what that is, it implies marginal independence. So if I have two nodes, A and B, and there's no path between them, then I would expect to see them not be associated in the data. All right, so first, what is a path? A path now is just any kind of going along a series of edges with or against the arrows. It's just the generic term path. So there's a path from C through X to Y. For example, a path C to Y to X. These are paths. And so we had talked about something called unblocked. And so a collider is this situation. We have a variable, a node, and the path goes into and out of that node through arrowheads. And so if you think about the basketball example, we had tall was a predictor of X. We had got game was a predictor of X, being about a professional basketball player. That variable X with respect to this path is a collider, right? They collide. And so here we have a situation where we have X and we have Y, and there's no causal relationship, but we have this path and it's unblocked, so it doesn't have a collider on it. So I can go from X, I can go to C to Y, and it's an unblocked path. And if there is an unblocked path between X and Y, or any two nodes, then I would see, if I calculated in my data, I would see some association between X and Y. It's just not a causal association. It's created by the presence of this confounder. And so there's an algorithm for identifying these confounders, which is you erase all the directed edges emanating from the exposure. So I have an exposure, which, say, for example, is treatment or being randomly allocated to treatment. So I erase all the edges emanating from the exposure. I identify all the unblocked backdoor paths between exposure and outcome, the outcome of our study we're interested in, whether it's blood pressure or death or whatever. Okay, so a backdoor path then is a path that goes from our outcome, maybe blood pressure or death, back through to get to the exposure. All right, that is a backdoor path. And each backdoor, unblocked backdoor path, that implies confounding, right? So we adjust for that by controlling for that variable along the path. So in other words, we remove the confounding by controlling for and adjusting a variable along that path. and we could experimentally control it by holding that variable as fixed. So just do, for example, a study. If we're doing an animal experiment, we do a study of only male rats. That would be control for sex. Or we adjust for it in a statistical model. And so we do that, and we can adjust, importantly, for multiple paths with just one variable when that happens. So if we look at this example, we have an exposure here, and we're asking, is it a cause of disease? And we have two other variables in the graph, C and A. Right? We erase all directed edges emanating from the exposure. So we do that. That's step one. So we still have arrows pointing to it, but we've gotten rid of the arrow pointing away from it. We identify the unblocked backdoor paths. And what we have here is D to C to A to E, and D, C, and E. Right? Those are the two unblocked backdoor paths. And so if we were to look at the crude or marginal association between E and D, we would see one. We would see that these two things are correlated or associated with one another. But that is explained by the presence of these two unblocked backdoor paths. There's no cause from E to D. And then what we do is we adjust or control for one of this variable, C, and it blocks both of those unblocked backdoor paths. It removes their confounding influence. And so now whatever I measure as an association between E and D, I'd feel more confident to conclude that it's a cause. The other tricky thing comes in with the colliders. Now sometimes you'll need to adjust for a collider. And I said before, when we adjust for, we select, like we do a study of only basketball players, which is to control for basketball players, then we'll see an inverse relationship between E and D, for example, which is not good. So here's an example where we have E, is it a cause of D? Well, I have B, C, and A to think of. And I have my unblocked backdoor paths, so I can go from D to B to C to E. I can go from D to C to E. And I can go from D to C to A to E. Right? I can't go through here because it's blocked by the collider. Now, in each one of those paths, we had C. So it makes sense we'd adjust for a control for C to remove the confounding caused by these unblocked backdoor paths. But when I do that, the fact that I've adjusted for a collider is then going to create an association. So what we call C is called S. And so S is the sufficient set of variables needed to adjust for confounding. Once you've identified S, which in the previous example was C, then you would draw an edge to connect all pairs of variables with a child in S. All right, so that's what we're doing here. I've adjusted for C, which is our set of sufficient variables to adjust for, and then, but there is a pair of variables with a child in that sufficient set, which is C. In other words, the two shared causes of C, A and B. And so then what we do is we draw an edge to connect them and then identify any new unblocked backdoor paths. And so in that example, we would have a new unblocked backdoor path from D to B to A to E. And so then I would need to adjust or control for one of these two things to get rid of that source of confounding. So that means we can identify an optimal sufficient set for adjustment, the minimum number of things you have to do. Now, as an epidemiologist, when we're doing observational studies, this idea of trying to figure out what to adjust for in order to remove confounding is the hardest part of that job by far, from an intellectual point of view. And it's the thing that observational data, although I use lots of observational data and we do the best with it we can, the problem is that when we're building our DAG, the DAG is only useful to the degree that it reflects reality, and we don't know that our DAG reflects reality. And the main thing is we don't know if we're missing variables that could also be creating confounding. Right? We don't know if every real unblocked backdoor path is present in our DAG, and if we don't know it's there, we don't know how to adjust for it. And so there's always this risk of bias. Now we can put bounds on that. We can be clever about it. We're not helpless. But generally, when we get done with an observational study, it's usually quite difficult to make conclusions about cause because of this threat of what we call unmeasured confounding. Where the DAG helps us understand the randomized controlled trial is this. So step one is if we have X, and X, variation in X, which we're going to say is our treatment, if X is randomly allocated, then there obviously are no arrows to X. if I'm allowing some random mechanism to determine who gets treatment and who doesn't, then there are no causes of getting treatment. And if there are no causes of getting treatment, it doesn't matter how many things also cause our outcome. There's no unblocked backdoor pathway. There's no way to get from Y to X. Right? I don't have to know anything else about Y. I don't have to know anything else about the system. If I know for a fact that X was randomly allocated, then I know there are no arrows pointing to it, and thus any association it has, it is going to be causal or just due to a small sample size and random fluctuations in data. And so we have statistical inference to handle that second problem, but our causal inference problem is pretty much solved. And so this is why when Bradford Hill was introducing randomization not as a statistical tool but as a causal inference tool, it was to help people divorce the decision about who got what treatment from characteristics of the patient in front of you. So maybe the sicker people would go on to the treatment, the new treatment, because they had more need for like a radical, shot in the dark hope. Or maybe the healthier people would get the treatment disproportionately because they would be maybe able to handle unknown side effects. So once upon a time, you'd have clinicians who were deciding who got the new treatment, and there would be causes then of why people got the new treatment that would then be associated with the outcome. So there would be confounding. And the other thing it does, randomization does, as Stevenson calls it, utmost good faith. Right? If I can prove and show that we've rigorously randomized, then that's a clear and transparent way of doing things that everyone can see happens and agrees on. There's no cajoling or we don't have to trust anybody. Right? We see the randomization happen, and we'll talk about that in a whole unit on randomization. We have ways of documenting that randomization happened. And so once randomizations happen, then I can be really confident if I'm happy with the statistical inferences, then I could be really happy concluding that what I'm looking at is actually a cause. And another really useful thing to use the DAG for in the context of a randomized controlled trial, and actually we'll come into this the next module, some other stuff, is it helps explain why we do intention to treat analysis. Right? So if I think about a DAG where I have an outcome Y, I have X, which I'm going to say is my random allocation to treatment, and I have TX here, which is the actual treatment. So what we often have in a study is we think of a two-arm parallel trial. We randomize people to a new treatment or to a placebo control. And then the people who get the new treatment, among those randomly allocated to that group, some of them do a better job than others actually complying with the treatment regime. Some of them will take the treatment and some of them won't. And some of them might drop out of the study based on effects of the treatment. Things happen post-randomization. So this line here, I randomize whether you're allocated to get the treatment, but whether you actually take it or not will have other things that predict that. Right? Your compliance or ability to actually take the treatment will have predictors, and those predictors might be associated with Y. And so when we're doing a randomized controlled trial, we shouldn't often calculate this association between who actually got the treatment and Y. We should always be calculating, at least to start, the association between X and Y. Right? Because this relationship is potentially confounded and in ways that we can't necessarily adjust for, whereas we know the XY relationship won't be confounded. Now, there's a trade-off there, because if people in my treatment arm aren't taking the treatment, then obviously if it's having a positive effect on average, I'm going to get a watered down, association. I'm going to get a watered down estimate of that. But that's the trade-off we usually accept in order to confidently conclude that there's no bias explaining that association. So this is where DAGs help to explain intention to treat. All right, so that's the basics of causal inference of using DAGs. We're going to come back to this in the unit on outcomes when we start to talk about the average treatment effect and why we use it and how that's based on essentially comparing two groups that we think are comparable. And we'll relate that back to DAGs when we get there. All right, thank you very much.